In example 2, we have some sort of tow train pulling a cable, which will pull another train with a force of, looks like 37,000 newtons to the left. The train experiences a resistive or frictional force of 180 newtons to the right. Determine the acceleration of the train. The train is our system. So this whole thing is our system, which means we're going to have to figure out the total mass of that system, and we've got our cable there pulling on the train. Okay, so we don't really need a sketch too badly here because we've already got our picture, nice little diagram there. Our coordinate system does need to be shown, positive we'll say that way. Our givens, we know that, well, we have our mass of our caboose, which is the mass of the red guy. And the mass of each car is given there as 1050 kilograms. No conversions have to be done, but we do need to state our unknowns. We're looking for the acceleration of the train. We have our tension force, which is 3.7 times 10 to the 4 newtons to the left. And our friction force, which is 1.8 times 10 to the 2 newtons to the right. And our total mass will be 1301 plus 2 of those 1050s, which is, one moment, 3401 kilograms. All right, so we're asked to find the acceleration. We know Newton's second law. Let's go ahead and draw our interaction diagram now. So our system is the train with everything. It interacts with the tow train, I guess you would say, through a tension force in that cable. Gravitational force with Earth, as usual. We have our normal and our friction force with our tracks or our ground, depending on where this train was. And there you go. For our forces, we've got normal force up, gravitational force down. Those are equal size because we're not accelerating in the vertical direction. In our picture, we have our tension force here, and it's much greater than our friction force. And we are accelerating in that direction. So we're going to say that our positive convention is going to go like this, up and left. Alright, so with that in mind, we're going to now describe what's happening to the train. So we can say that the train accelerates in the positive direction due to the unbalanced force Ft greater than Ff in that direction. Point particle, constant acceleration. Estimation here. Can we do it? I don't know. We might need a calculator. So 40,000-ish. Take away 200. Was that 38,800? Divided by 3,400. So 38,000 divided by 3,400. So that's about 10 meters per second squared. About. I know that's always the hardest step. Don't worry about it, you'll get better as you go. All right, let's solve the problem. First step, write out the F-net equation in the direction that you're considering all your stuff. And that's the x direction here. So our positive was to the left, so we're going to go Ft, take away Ff. And now we have to ask, does that equal 0 or does that equal ma? Well, we know that this thing's accelerating, so we have to set it equal to ma. So here's our equation, which we're going to manipulate and solve for. What is it we're looking for? A. So A equals Ft, take away Ff, all divided by m. And this is the total mass, so we're going to go 30.7 times 10 to the 4 newtons, take away 1.8 times 10 to the 2, all over 3401 kilograms. And that equals 10.83 meters per second squared. We have to put two sig figs here, so we're going to go the train acceleration is 11 meters per second squared left. So it's speeding up in the positive direction because of this tow train. Let's just have a view of what this looks like. So to reiterate, F-net equation, F-net equals ma, because it's Newton's second law. This thing is accelerating. The unbalanced force is because of the greater tension force than the friction force. Rearrange for A, sub in your numbers, equals 2 significant digits from the question, and our final statement. So you can practice this. I'll post some solution sheets for you to practice this through. Textbook page 133, 1 to 6.